Okay. Good afternoon, everyone. It's our pleasure, it's our honor to have Richard Stanley to give a talk today. And Richard Stanley, I'm pretty sure everyone knows him because he's like a very prominent mathematician. His work just influenced so many different people and continually just like affecting like so many generations of students. And even our previous speaker, Sheila, and also Sergey, were actually Richard Stanley students, and they give wonderful talks. And so like, if I have to speak more about like the award and the books that Richard Stanley is like written, I have to spend another hour. So instead of doing that, let's give the time to Richard Stanley. So today he's going to tell us the XDes sets of a permutation. So all yours, Stanley.
Okay. Thank you, Anna, for the introduction. I'm going to talk about a generalization of the ordinary descent set of a permutation, which is a very standard statistic on permutations. This development is going to be based on symmetric functions. So for those not so familiar with symmetric functions, I'll just say a couple of words about them first. So by a symmetric function, I just mean a formal power series of bounded degree in infinitely many variables, x1, x2, etc. Let's say with rational coefficients. And then symmetric would mean that it's invariant under any permutation of the variables. Not really a function, it's a formal power series. So for instance, the sum of the nth powers of the xi's would be a homogeneous symmetric function of degree n. The second line is the third elementary symmetric function, homogeneous of degree 3. And the sum I less than j xi squared xj would not be symmetric, whereas x1 squared x2 appears, but x1 x2 squared does not appear. Well, as we'll see, it's natural to index some symmetric functions by partitions of a non-negative integer n. So that will mean a sequence lambda 1, lambda 2, etc. Weakly decreasing sequence of non-negative integers whose sum is n. So only finitely many of these lambda i's are greater than 0. So most of you know, I mean, that's going to be 5 partitions of 4. Here they are. Essentially 5 ways to write 4 as a sum of positive integers without regard to order. It's easy to see that the space of donated lambda super n of all homogeneous symmetric functions of degree n is a vector space over the rational numbers. This dimension is the number of partitions of n. So we index different bases of this vector space by partitions of n. And only one basis is really going to be importance in my talk. These are the power sum symmetric functions. So p lambda, where lambda is some partition of an integer n. We can define that by p0 equals 1, pn, by pn I mean the partition with one part equal to n is the index. That's the sum of the xi's to the n. And for an arbitrary partition, lambda, well, p is a multiplicative basis, p lambda is p lambda 1 times p lambda 2, etc. So it's not hard to see that these p lambdas for lambda, a partition of n, is a vector space basis for the homogeneous symmetric functions of degree n. This would be the case n equals 4. There's 5 partitions of 4, so we get these 5 power sum symmetric functions which form a basis. And here's an example of a expansion of a symmetric function, the third elementary symmetric function in terms of the p's. Of course, since they're a basis, every symmetric function will have a unique expansion in terms of power sums. You can see well, in some sense, this is not a nice power sum expansion because some coefficients are negative and they're not always integers. Like here, none of them are integers. We'll see some examples where we do have integrality and positivity. Now, I should mention, this is just going to come up in one example. Another basis for symmetric functions are the famous Schur functions, denoted S lambda. This is maybe the most interesting and important basis, and it has connections with all kinds of other areas of mathematics. Well, I won't define it here, but only for one example will I be expanding something in terms of Schur functions. Now let's recall what I mean by the ordinary descent set of a permutation. So I think of a permutation W as a word, a sequence A1, A2 up to AN. The numbers 1 up to N, each appears once. This is a Proctor SN, a symmetric group of all permutations of 1 up to N. The descent set of W, denoted SW, is a set of all indices from 1 to N minus 1, such that AI is greater than AI plus 1. Very important statistic on permutations. For instance, here's a permutation of when N equals 7. After in red are the numbers whose index is a descent. 6 is followed by a smaller number, so 2, the position of 6 is our descent. The descent set is 2, 3, 5. Well, what we would like to do is we'll understand how many permutations in Sn have a given descent set. dw equals S, or some fixed S, set S. We'll call this beta n, and we'd like to sort of encode this information, or the value of beta n S, by a generating function. So we'd like some kind of object that records this descent set W, the set S, sum over all W and S and Y dash W, or equivalently, sum over all subsets of bracket n minus 1. This means it's set 1, 2 up to n minus 1, beta ns y sub s. These y sub s's should be linearly independent, so if we have this sum, we can recover the coefficient beta ns. If you think, if the indexing set instead of sets here, or say non-negative integers, then we could use something like x to the n. So what should be the equivalent of x to the n indexed by sets? Well, there's all kinds of possibilities, and the one that works best here are what's known as fundamental quasi-symmetric functions due to Ira Gessel. If we fix our positive integer n and let s be a subset of 1 up to n minus 1, then we'll define this power series in infinitely many variables. It's homogeneous of degree n. Fs, it's a thing, you look at all weakly increasing sequences of positive integers, I1, I2 up to In. But then there's a condition where we must have a strict increase of Js and S. And this object would be denoted by Fs, fundamental quasi-symmetric function. It's not a symmetric function in general. For instance, in n equals 3, well, by definition, F1 would be the summing over all sequences A less than B less than or equal to C of positive integers. There's a strict inequality here because it has to occur after the first place, this 1 here. XA, XB, XC, you see that X1, X2 squared appears, but not X1 squared, X2. You can't have 2 1s. That's the first two, smallest two indices have to be different. So this generating function we want for this that records how many permutations have a given descent set, sum over W and Sn F indexed by the descent set of W. It's a basic theorem that this is just the sum of the xi's to the n, the first power sum to the n. This illustrates why these FS's of the right, or at least a good indexing set. So I will not prove this, but instead we'll look at one example. N equals 3. There's 6 permutations in S3, and I've written down the corresponding fundamental quasi-symmetric function. Here there's a descent in the second position. 2 is in the descent set. So there's a strict inequality here after the second number. So you have all these symmetric functions, quasi-symmetric functions. They're not always symmetric, but their sum is a symmetric function, sum of the xi's cubed. So now let's generalize to x descent sets. We're going to specify which pair of consecutive terms in our permutation we're going to regard as descents. So will that X be any subset of the set script En, the set of all pairs ij between 1 and n, where I does not equal j. An X descent of our permutation W is any index k for which, the 2 consecutive terms ak plus 1 are in X. And of course, the X descent set, which is XDes W, will just be the set of X descents. So for example, if X consists of all pairs ij where I is greater than j, then the X descent is an ordinary descent set. You have an ordinary descent if after those terms ij for which I is greater than j. So the X descent set generalizes the ordinary descent set. I don't require an I be less than j here. I could be greater than j also. If X consists of all possible pairs, I not equal to j, then every pair ij is an X descent. So the X descent set of any permutation W is 1 up to n minus 1. Okay, are there any questions about these definitions? And let's try to find a generating function for the X descent set, or at least define one, completely in analogy with ordinary descent sets. I'll let Ux be the sum over all W and Sn, fundamental quasi-symmetric function indexed by the X descent set. As a historical note, I could say that Ux is a specialization of a symmetric function considered by Tim Chow in 1996. But he and some other people who looked at it sort of went in a different direction than I'm going to do here. So here's an example. When n equals 3, we'll take this X descent set. 1, 3, 2, 1, 3, 1, and 3, 2. Note we have both 1, 3, and 3, 1 X descents. Here's the 6 permutations in S3. Here are their X descent sets. The X descents for 1, 3, 2 is 1, 2, because 1, 3 is an X descent, and 3, 2 is an X descent. So Ux by definition is one X descent set equal to empty, 1 equal to 1, 1 equal to 2, and 3 of them equal to 1, 2. Well, it turns out that this linear combination of quasi-symmetric functions actually is a symmetric function. When you expand it in terms of power sums, where you get integer coefficients, but we do have a negative coefficient. So is anything going on here? Is just some random fluke for this example. Well, the first theorem, so it's an easy theorem, is that ux is always p integral. If you expand it in terms of first and a symmetric function. If you expand it, that's a well, first of all, it's the symmetric function. And if you expand it in terms of the power sums, the coefficients are integers. Well, let me sort of explain with an example why it's going to be a symmetric function. Well, I'm going to consider, assume n equals 7, and I'm going to look at the coefficient of the monomial x1 squared, x2 cubed, x4 squared, and I would like to sort of pair, when this monomial appears in one of these quasi-symmetric functions, I would like to pair it with some quasi-symmetric function where the monomial appears when you interchange 1 and 2 in these indices. So here I've repeated the definitions of ux and fx. Suppose our permutation w is a1, a2 up to a7 in the sum. Remember, this fs for any s is just the sum of distinct monomials. So either this monomial will appear with coefficient 1 or 0 in fs. So when does it appear in fs? Coefficient 1 in x descent set. Well, by definition, it has to be when a1, a2, a3, a4, a4, a5, and a6, a7 are not in x. They're not allowed to be x descents. For instance, if a1, a2 were an x descent, that would mean we would have a strict inequality between I1 and I2. So there's no way we could have the smallest index repeated. We could not get an x1 squared. And similarly for these other exponents. Okay, I've repeated that sentence. This is the condition for the monomial to appear in this quasi-symmetric function. Now we'll factor w according to the largest factors that have no x descent. I should the largest factors that these pairs that are not allowed to be in x are consecutive elements in the factors. A1, A2, A3, A4, A5, because A3, A4, and A5 were in x, and then A6, A7. We just factor that as a product of words. Well, I've now, if I interchange U1 and U2 here, 1 and 2, and look at the word W prime equals U2, U1, U3, that is A3, A4, A5, A1, A2, A6, A7. Now the monomial x1 cubed, x2 squared, x4 squared will appear. Originally it was x1 squared, x2 cubed, interchange 1 and 2. So now this will appear because we have no x descents in x, A3, A4, A5, so we're allowed to have an x1 cubed. Similarly for these other exponents. Well, this sort of pairs off a term where an fs, where x1 squared, x2 cubed, x4 squared appears, and what you get when we reverse 1 and 2. And if we generalize this argument, you see that ux is a symmetric function. That's the idea. Then some similar reason, which I will omit, which has to do with the freedom you have when you have these exponents greater than 1 here, will show that ux is also p integral. So that's my first theorem. Ux is a p integral symmetric function. And the second easy theorem is the effect of this standard linear transformation on symmetric functions. That's a basic part of the theory. Here I can define, this is not the usual definition, this is usually theorem. But I'll just define it by saying omega on the power sum symmetric function P lambda is a certain sign -1 to the n minus length of lambda. Length of lambda is the number of non-zero parts times P lambda. And it's linear over the ration. So you extend the definition by linearity. So the P lambdas are eigenvectors. The eigenvalues are plus or minus 1. In particular, it's omega's involution, which is immediate from this definition. And an easy theorem, once you know a little bit about symmetric function, if you let x bar be a complementary subset to x, everything in En not in x, then omega ux is ux bar. So if we know the power sum expansion of ux, we just change some signs and we get the power sum expansion of ux bar. Okay, so now let's look at a special case where we can say quite a bit more about the power sum symmetric function. If we have a permutation W, I'm going to define the record set. We think of a record as an element larger than any other. We read the permutations from left to right and see when we set a new record, we find a new element larger than any previous one. So the record set is defined to be those indices I for which AI is greater than AJ for all J less than I. And sort of by vacuously, 0 is always considered to be in the record set. To form the record partition, you look at the record set. This subscript means there are either in increasing order, and we look at the differences between consecutive terms and a final difference n minus rj. We take these differences and arrange them in decreasing order. We'll get a partition of n. And that is the record partition. So here's a conjecture that made by me and later proved by Ira Gessel. Suppose X has the property that allow descent, what we consider a descent, that if J is an X, then I is greater than J. In other words, every X descent is an ordinary descent. X descent set is a subset of the ordinary descent set. The UX has this explicit combinatorial expansion in terms of power sums. You look at all permutations in Sn whose X descent set is empty, the power sum symmetric function indexed by the record partition. So we've given a combinatorial interpretation of the expansion in terms of power sums. In particular, UX is P positive. Coefficients will be positive, non-negative. Yeah, repeated this theorem, and note that it's saying that if we know the distribution of the X descent set on all W and Sn, that's the information UX records, that's equivalent to knowing the distribution of the record partition on all W with empty X descent set. Kind of surprising. What do the record partitions on permutations with empty descent set? Why is that information the same as the distribution of X descent on all partitions? But this shows that information is equivalent. Here is an example. I've taken n equals 4, and I'm coming back to, well, this example generalized to any n where we have descents only at consecutive integers, 2, 1, 3, 2, and 4, 3. Actually, later I'll look at increasing pairs of consecutive integers. But, here, the UX will be the same. Anyways, here are the 11 permutations with X descent set that are empty. No integer I is followed by I minus 1. In blue are the records. The largest numbers are see reading left to right, and then the record partitions, the differences between those blue indices in decreasing order. 2, 4, 1, 3, we get 4 and 2 differ by 1, and then 4, 1, 3 is a sequence of length 3 before we get to the end. So 3. So UX will be P1 to the 4th, and there's 3 2 1 1s here, so we'll get a 3 P2 P1 squared, etc. So this is UX. Well, Gary Grinberg, who was my collaborator on much of this work, and also did a lot of nice independent work, which I will be mentioning, proved a more general result that if whenever you have ij in X and ji is not in X, then Ux is P positive. And in my previous theorem was only when ij is in X, then I is greater than j. This is even more general. And Grinberg has a combinatorial interpretation of the coefficients, but it's pretty complicated. Not so elegant as these record partitions. I won't mention it here. Okay, so now let me give one example where UX is very nice behavior. And this is what I mentioned before. We'll just take X. It consists of all pairs I plus 1, 2, 3, 3 up to n minus 1 n. These are called successions. Permutation with no successions, whose X descent set is empty, is called a succession-free permutation, and these were studied long ago, and the number of them is of the node point Fn, and it was known that the generating function for these Fn's, this exponential generating function with this shift in index, e to the minus x over 1 minus x squared. So here's my theorem. This is the one-time sure functions come into my talk. Ux is a very simple expansion in terms of sure functions. These are the so-called hook sure functions. There's one part greater than 1. One part, well, the most one part greater than 1, I, and all the other parts equal 1. These are called hook sure functions. And the coefficient of the hook I, 1 to the n minus I, that is n minus I parts equal to 1, is just Fi. So this symmetric function encodes all the number of permutations in Sn with a given succession set. For instance, this is what it looks like for n equals 4. These coefficients 11, 3, 1, 1 are just these coefficients 11, 3, 1, 1 here. These are the subscripts of the hook shapes. Well, let me sketch the proof. What I'm going to do, I'll pick my subset S of 1 up to n minus 1, and I want to expand both sides in terms of fundamental quasi-symmetric functions and take the coefficient Fs on both sides. Now, by definition, on the left-hand side, we're going to get the number of permutations with X descent set, that is, succession set equal to S. Now, what makes everything work out so nicely here is that when the Hook-sure functions have a very simple expansion in terms of fundamental quasi-symmetric functions. Si 1 to the n minus I is just the sum over all Fs, where S has n minus I elements. So in particular, each Fs appears in exactly one of these terms. If S has n minus I elements, then it appears in the Si 1 to the n minus I term. So what we need to show is that Fi is the number of permutations in Sn whose X descent set W is S, if S has n minus I elements. So this is says two sets have the same number of elements. We can give a bijective proof. Here's what we need to show. number of permutations with succession set S is the number of permutations of length I with no successions. This is the bijection between these two sets. Now I'll just illustrate it for 5, 6, 4, 1, 2, 3, 7. This has succession set 1, 4, 5. Those are the positions, up to the first position, I is followed by I plus 1. 5, 6, 1, 2, and 2, 3. So N is 7 here. I is 4. Because the cardinality of S is N minus I. We're going to factor W according to the longest consecutive, longest sequences of consecutive, increasing sequences of consecutive integers. So we're factoring it after the non-successions. And now we take the smallest, the factor with the smallest terms, 1, 2, 3, replace it by 1. And the factor with the next smallest terms, 2, replace it by 2, etc. So we'll get this permutation 3, 2, 1, 4. And it's very easy to check that. This says empty succession set, no successions, and we can just reverse all these steps. So that's the bijection. Okay, any questions about that? It also has a nice Q analog, which I won't discuss here. Because I'm going to now change the subject to getting a different kind of angle on succession sets. I mean, not on X descent sets. By thinking of X as a digraph. I think graph theoretically. So let's think of X as a digraph with edge from I to J, directed edge from I to J, if IJ is an X. And I want to look at the connections between X descents and Hamiltonian paths in X. Well, we can think of a Hamiltonian path in X as just a permutation in Sn. The vertices of my digraph, 1 up to n. And the Hamiltonian path should be, should be a sequence of edges, or if you want a sequence of a permutation of all the vertices, such that there's an edge from A1 to A2, A2 to A3, etc. In other words, such that AI plus 1 is an X, all I between 1 and n minus 1. So, in other words, a Hamiltonian path is just a permutation whose X descent set is 1 up to n minus 1. Every pair is an X descent. Every pair consists of X descent. Let's ham X be the number of Hamiltonian paths in X. Okay, so I'm repeating this observation. W is a Hamiltonian path if and only if its X descent set is everything. Similarly, W is a Hamiltonian path in the complement if and only if its X descent set is empty. This would be a Hamiltonian path in the complement if none of these pairs were a directed edge in X. So the X descent set would have to be empty. Well, from that, we can see how we can read off the number of Hamiltonian paths in the complement and also in X in terms of UX. We expand it in terms of power sums, and ham of X bar is just the sum of these coefficients. So it's just an easy keeping track of the definitions. This was a definition of UX, sum of F X descent set X. Remember, a permutation is a Hamiltonian path in X bar if and only if the X descent set is empty. M of X bar is the number of permutations with empty X descent set. And now we'll take the coefficient of X1 to the N on both sides here. Check very easily that the coefficient of X1 to the N in Fs is 1 if S is empty, and 0 otherwise. I mean, that's immediate from the definition. The only way we get all these X, N X1s is where there be no strict increase in the I1, I2 up to IN. So it defines Fs. The coefficient of X1 to the N in P lambda, definition you see immediately is 1. And putting all that together, taking the coefficient of X1 to the N on both sides here of this expansion of UX in terms of the power sums gives exactly this thing. And as a corollary, we get the expansion, we get the formula for the number of Hamiltonian paths in X in terms of the C lambdas. Because UX, well, we just take X, turn X to X bar. You apply omega to this formula. And X would be UX bar, and C lambda becomes, P lambda becomes -1 to the N minus L lambda P lambda. So when we apply the previous theorem to X bar, we'll get ham X is this sine sum of the C lambdas. Okay, can we do anything with this result? Well, one thing we can do immediately is the theorem of Cloud Bears. He showed that for any digraph, the number of Hamiltonian paths in X and the number of Hamiltonian paths in X bar, the complement, are congruent mod 2. Well, if UX, so this is an observation of Dari Grinberg, if UX is the sum of C lambdas, then our interpretation of ham X and ham X bar amounts to showing that these two sums are congruent mod 2, which of course is trivial because the signs -1 to the N minus L lambda is congruent to 1 mod 2. So Berzier's theorem is immediate. So what more can we do with that? Right, digraph. So let's look at a special case, tournaments. We call the definition of digraph X on vertex set 1 up to N, such that for every pair of distinct vertices, there's exactly one edge between I and J, either I to J or J to I. Okay, now for any permutation in Sn, we'll let rho W be the partition of N whose parts are the cycle lengths of W. W is the identity element. Rho of W would just have N parts equal to 1. Every cycle is length 1. So here is Grinberg's expansion of UX when X is a tournament in terms of the power sums. Completely different kind of expansion than the one I gave before in using record partitions. We're going to sum over all permutations of W of odd order. Every cycle length is odd, such that every non-singleton cycle of W is a directed cycle of X. In NSC, that stands for non-singleton cycles, is the number non-singleton cycles in this permutation W. Number of cycles of odd length, well, you all have to have odd length. Number of cycles of length greater than 1. And the power sum symmetric function indexed by the lengths of the cycles of W. By the way, as a corollary, I'll give an example in a second, quite a remarkable formula. Notice that UX not only is a polynomial in the power sums with integer coefficients, well, actually, there's non-negative integer coefficients. It's a polynomial in the odd power sums, because only odd cycle lengths are allowed in W. And since we have a factor of 2 for every cycle of length greater than 1, it's actually polynomial of integer coefficients in P1, 2P3, 2P5, 2P7. An example. This tournament, I've written the edges as the pairs. These are the elements of my set X. It's 1, 2, means there's an edge from 1, 2. What are the allowed permutations here? Every non-singleton cycle is of odd length and is a directed cycle. In the graph G, there's these 3, but always the identity permutation would be allowed, and that'll always contribute a P1 to the N. There are no non-singleton cycles, and all the cycle lengths are equal to 1. And 1, 2, 4 is a directed cycle. 1 to 2 to 4 to 1, 3, 4 is also a directed cycle, but for instance, 2, 3, 4 doesn't appear here because, you know, 2, 3, 4 is a cycle, but it's not directed. So U of X would be P1 to the 4 plus 4P3 P1. These factors 2 to the number of non-singleton cycles, 1 and 2 to the 1 each factor. Okay, so I repeated my formula for ham X in terms of the C lambdas. I've repeated the expansion of UX in terms of the P lambdas for tournaments. So if we just put these results together, we see the number of Hamiltonian paths in X. Well, actually, trivially for a tournament, that's the same as the number of Hamiltonian paths in X bar, because we can just take a Hamiltonian path in X, reverse all the arrows and get a Hamiltonian path in X bar. But it's going to be the sum of all of these allowed permutations 2 to the NCS number. Okay. Repeated this result. Why is this true? I'm just using the fact that it's easy to see for any X. If you look at expand UX in terms of the P lambdas, then the coefficient of P1 to the N will be 1. Oops, just look at this expansion of UX in terms of look at the definition of UX in terms of the quasi-symmetric functions. If the coefficient of X1, X2 up to the of Xn on both sides, and this result pops out. So we conclude a theorem of Rede, 1934. Every tournament has an odd number of Hamiltonian paths. Right, because for the identity permutation, we always get a 1 here in this sum. Any other permutation, well, it's going to have at least 1 odd cycle, so we're going to get a 2 to some positive path. And in fact, we can even get a stronger result, mod 4 expansion for a tournament X with X odd directed cycles. It's directed cycles of odd length. The number of Hamiltonian passes X is congruent to 1 plus 2k mod 4. Because this exponent is 1. Every time we have a single odd cycle, we just take it as a cycle of W and set all the other, and make all the other vertices singletons. So we're going to get a 2 for every odd cycle. 2k And all the other permutations have at least 2 odd cycles, so we get a factor divisible by 4. Okay, so nice extension, red H result. Okay, maybe I can finish with some sort of open-ended problem. I mean, I think there's quite a bit more to look at in the subject. Some things I haven't mentioned at all, like connections with chromatic symmetric functions. But here's something that looked like it could be interesting to look at further. I'll remind you of the definition of the combinatorial definition of the Eulerian polynomials. So for any permutation in Sn, dash W with a little d is the number of descents of W, the cardinality of the descent set. The Eulerian polynomial an of q is the sum of all W and Sn q to the dash W's. The generating function from permutations in Sn according to the number of descents. But sometimes you'll see another +1 in this exponent. If we're here, we might as well forget this extra +1. Well, there's many things you can say about Eulerian polynomials. Let me just mention one theorem that you can think about generalizing. That all its zeros are real. And it's well known, since it has positive coefficients, that its coefficients are log concave and unimodal. Well, obviously, we can extend the definition of Eulerian polynomials to x descents. For any permutation in Sn, XDes will be the number of x descents of W. And we can define an x-Eulerian polynomial, XAN_Q, exactly analogy with ordinary Eulerian polynomials, generating function for permutations in Sn according to the x descent set. Can you say anything interesting? Unexplored territory. The ordinary Eulerian polynomial is easy to see by looking at a permutation in its reverse, that the coefficients are symmetric. They read the same backwards as forwards. This need not be true of XAN in general. It will be true if X is a tournament. The same proof works. We can read them. Look at the reverse of the permutation. Consider what happens. Here are, for instance, the X Eulerian. There are 4 non-isomorphic 4 vertex tournaments. Here there are 4 X Eulerian polynomials. One of them occurs twice. One is the ordinary Eulerian polynomial. That's when we look at transitive tournament. That would give ordinary descents. There's an arrow from I to J if I is less than J. So I'll get ordinary Eulerian polynomials. Twice you get this very nice factorable polynomial. And then the other one, the zeros are not real, not always real. Although it is unimodal and log concave. So what can you say in general? You've looked at some random examples, and we always had log concavity, which would imply unimodality since we have positive coefficients. When do we get nice factorizations? When do we get real zeros? Not just in the tournament case, but we look at any X. I noticed that there was some example where we got Eulerian polynomials that was not a transitive tournament. Why was that? Why is that? Okay, so I think with this note, I will conclude my talk. Thank you for listening.
Thank you so much for Richard's talk. Let's thank the speaker.
Thank you.
Thank you. So any questions?
May I ask one question? I have also posted in the chat. So do some of the results have refinement that record a number of inversions as well? So it's like throwing in a vector.
Oh yeah, that's a very good question. In order to find the Q analog, I mentioned that for succession free permutation, so it's a very nice Q analog. It turns out in the definition of UX in terms of quasi-symmetric functions, we should throw in Q to the number of descents of the inverse permutation. Now, in general, if you look at, we've looked at Q to the major index, Q to the number of inversions, Q to the number of descents. In general, it doesn't look nice. There are some examples where you get nice behavior. One is because there's a connection with, which I didn't go into, with chromatic symmetric functions and the Shirashian wax, Q analog chromatic quasi-symmetric functions. But it seems like most of the time it's not going to be nice, but maybe there are some special cases worth considering. Thank you for the question.
Thank you. Yeah, I have a work on like something to this flavor, so I might send an email later and to talk more about this. Okay.
You said you sent me an email?
I will email later. My name is Yifeng.
Okay, I'm sure I'll take a look.
Thank you.
Any other questions for Richard?
Yeah, I had a question, Richard. I'm sorry, my audio doesn't seem to be working very well, so I hope you can hear me.
I can hear you.
Yeah. So you had an expansion in terms of short functions with hooks, and I believe the coefficients were positive or non-negative anyway.
Yes.
Is that a representation that has shown up anywhere else?
Well, the sum of all hooks, I think that's the action of Sn on the exterior algebra.
Right, but you had multiplicities, right?
Well, I had these factors of Q. Yeah, that's, oh, no, you're right. Oh, no, I have these multiplicity. Oh, yeah, you're right. Oh, no, that's a good question. That question occurred to me too. Actually, now that I recall. Yeah, I don't know. That is a good question.
Thanks.
Yeah.
Any other questions for Richard?
I should say to Sheila that there was a Q analog of this succession-free generating function where you also had Q to a power, I think, the number of descents of the inverse permutation, and that was also had positive coefficients. You could even ask for a representation theoretic interpretation of that refinement.
Right. Thank you.
Is there any way to extend the ideas you discussed to Hamilton circuits in these digraphs?
Well, you could. I don't looked at that, but you just need one other pair being X descent, the last element of the permutation in the first. So yeah, you could read off the number of Hamiltonian circuits, I think. I think Dari wasn't able to come up with anything, interesting, comparable to Berger's theorem and Rede's theorem. But yeah, somebody should take a look at that. Another thing, maybe worth taking a look at, although I couldn't get anywhere with it, is the famous conjecture of Lovász that every vertex transitive graph has a Hamiltonian path. If you replace, this is for non-directed graphs, but you can replace every edge by just two edges, one in each direction. And ask whether that digraph has a Hamiltonian path. So is there some way of getting vertex transitivity into the picture so that you could prove Logos's conjecture using this machinery? I mean, that would be fantastic, but I don't see how to do that.
All right. So any other questions? If not, let's thank the speaker again. So